Hi, welcome to this pre-recorded version of my talk for PyData Global conference. In this talk, I will try to compress several decades of evolution of data modeling and data processing into about 20 minutes, and also leave some time to take a small peek into the future. And I will be focusing on highlighting the key trends as I see them, and also the pitfalls and dead ends that some of them lead to. And most importantly, I'll try to build a common vocabulary between people with different backgrounds in data. My background is in software engineering and architecture, and I'm a long-time open data geek, now turned data startup founder. I've been on both sides of the enterprise data fence in OLTP and OLAP, and despite data being something that connects the both sides, I saw that the entire understanding of what data is on two sides is different, and this often results in a lot of tensions and inefficiencies. And to my surprise, I discovered that modeling time and how things change over time in data seems to be at the center of this problem. So we're going to take a look at data from both of these perspectives. So let's start with OLTP systems, as that's usually where the data in your company comes from. OLTP is your application, a service, or a product that client interacts with, something that provides external value to the customer. Imagine we ask an engineer to implement a simple marketplace service for an online video game to sell hats or whatever. This is roughly how the resulting database schema would look like. So we have some SKUs for sale at a certain price. Every SKU has one or several items. Our users have accounts and balances and inventories. I want to highlight that this is the default. Vast majority of engineers from junior to senior would implement it roughly the same, because this is how we're taught. This is how our school books and all of our courses present the solution to us all the time. This is, of course, a non-temporal model. There is no notion of time inside of the schema. The database stores the current state of our system. Instead of time, we only have state transitions that are done using the CRUD queries. So we deploy and run this application, and it's in active use, but how do we know what it's actually doing and how it performs? All these questions, like what's the currency earning rate, are not easily answered using our database schema. So this is where we realize that state is not as interesting as dynamics of change. And analytics is all about time, the dimension we specifically decided to ignore. This puts engineers onto a long and windy path of introducing the time into data somehow, and they invented many ways to do so. First two are just stopgap solutions that I just want to mention for completeness. So when the application is new and grows fast, engineers might not have time for any analytics, so they might say, well, we're already taking the database backups, so why don't you just diff them and see what changed from that data? This is obviously a terrible solution. The ETL is complex and data is very low frequency and lossy. You will not be able to, for example, reconstruct individual transactions from two backups taken one day apart. Changed values selection is just an iteration on top of that, where we add this last modified column into every table and can produce smaller but incremental updates. So in theory, we can increase the frequency of updates much higher, but at the expense of adding way more complexity to the solution that is still lossy, that still does not give us individual transactions. Then comes the big contender that you probably heard about. Change data capture assumes that for every production state table, we create a corresponding log table that will be capturing every single change to the state table that happened using either triggers or replication log. In engineers' eyes, this is a pretty cool solution because CDC is transactional and lossless. So engineer might claim that we have achieved the ultimate granularity. An analyst, though, might not be as excited because this is what they'll have to deal with. Using these log tables, they will have to play this what happened game. Here you can see that time t1 user balance has decreased by 100 and a new item was added into their inventory. So we kind of can infer that this was a purchase transaction and which SKU was bought. This is not a situation you want to be in. What we're facing here is information loss. What state changed doesn't really tell us why it changed. This is something we call anemic data. We see some numbers changing, but they don't tell us what happened from the business perspective. Your application is already doing a lot of this hard work to translate business transactions into state changes. By using state changes for analytics, you will end up recreating an inverse version of this entire business logic on the analytics side. So I really think CDC works on a wrong level where information has already been lost. It, for some reason, keeps re-emerging in data processing tech and often being advertised as the best way to extract data from prod databases. But I really think it only works on a few narrow cases and it's not a viable general case solution. Best solution is not to lose information to begin with. Domain events are a big step in this direction. In this model, application still stores its state in a database as before, but in addition to state transitions, it writes descriptive event records into something called event log. The difference with CDC here is that these events speak the language of your business. So our entire previous example can be replaced by a single, very descriptive event called SKU purchase. This solution, however, is pretty expensive to maintain from engineering perspective, as there's this duality between events and state inside of your application now that you have to keep in perfect sync. So this brings us to event sourcing, which flips the problem entirely on its head. Instead of storing state, the application now stores history, and the current state is reconstructed from history on demand, which is pretty easy to do, right? Having the deposit event for 1000 currency and later a purchase for 100, we can easily calculate that the current balance of the account is 900. In event sourcing, state can still be stored, but only as an optimization. Here we have the projector component that listens to the history that is written to the event store database, and it continuously updates the state stored in a projection database for us to be able to answer some of the queries much faster. Ingesting historical event data from the event store into the analytics requires almost zero work because it's already in the exact form that we need. So I believe that there's such a thing as good data. It's the data that speaks the language of your business. Learn to recognize and avoid anemic models. State is simply a projection of history. There's information loss happening by definition. It's not fit to be your primary data model. And there seems to be something very wrong with our defaults. Why losing history is okay for initial implementation? Why destructive updates are okay? I think we need to change how we teach data to new engineers, and it's time to realize that analytics is a core requirement, and as I showed you, it's not something you can bolt on later. Now let's see what meanwhile has been happening on the OLAP side. Analytics is usually about providing internal value to the business, providing insight that drive optimization and strategic planning. And the classic approach for a very long time was the star or snowflake schema, also known as OLAP cube and pivot table, that allows you very easily to slice, dice data, drill up and down, and it's said to be great if you have clean and well-structured data. At the center of the snowflake lies the fact table, a very dense table that stores event records. Here, for example, you can see marketplace transactions that occurred at certain times. This table is optimized for a very high rate of events and volume of data. Most columns here are the foreign keys to the dimension tables. The dimension tables, also known as slowly changing dimensions, have multiple different forms, most common of which captures change using effective time intervals. Here we see that SK1 costed 100 from T1 to T2, and then its price dropped down to 50. Dimension tables are said to be good for data that changes infrequently, but how frequent is infrequent? In our game marketplace, where prices might change weekly, that doesn't sound too frequent to me. But if it was Walmart or Costco's data warehouse, where prices can change hourly on thousands of SKUs at a time, this sounds pretty frequent to me. And when you look at this table, you might ask yourself, what's the reason behind the price change? Was it dropped because of a promotion, expiration date, or something else? So we're back to this anemic data problem again, knowing what changed but not knowing why. Whether you need to account for all this really depends on the nature of your business. Snowflake schema design highly depends on the questions that you will be answering using it. So this means that you have to know your questions and anticipate them upfront. In reality, you will most likely not get all of them right. So this, in combination with the schema being pretty hard to evolve, certainly caused its downfall and the rise of ELT and data lakes. Unlike ETL, extract load transform assumes extracting and storing raw data from the production applications with minimal preprocessing, and then using massive parallelism to analyze this data. If we combine this trend with event sourcing, a pretty magical thing happens. Data lakes become just big event stores. They extract and store same event histories, mostly unchanged, immutably, and forever. So this to me is a very cool indication of OLTP and OLAP data models finally converging into one. Temporality manifests itself not only in how we model data, but in how we process it as well. And this one is significantly less understood. I can confidently say that all of you are familiar with batch processing, because you do batch when you use Excel, when you query SQL databases, when you write scripts in Pandas or R. Its key characteristic is that it treats data as a bounded list of records. To understand it better, let's imagine that we need to produce the statistics on daily COVID-19 cases, similar to the one that you're getting on the news daily these days. We can do this by writing this SQL query that groups all cases by date and then counts the number of events per every group. And then we just run this script every midnight. To see what happens, we'll use bitemporal diagrams. So don't panic, they're pretty simple. On the x-axis, we have event time, the time when event happened in the real world. So for example, on Thursday, we see that there was 2 COVID-19 cases registered. On the y-axis, we have system time, the time when event entered into our system or into our database. In the ideal case, there is no delay between event happening in the real world and it entering the system. This gives us this nice diagonal. Let's see how our query performs in this idealized case. Remember that we're running the script every midnight. So on Thursday, it will give us 2. On Friday, it will give us 1, but it also will give us 2 again for Thursday since we're rerunning the query on the entire dataset, and so on. So this looks pretty nice. There's some redundant work there for sure, but it's not a big deal. Unfortunately, in reality, this is not at all how data looks like. Data often can be late, out of order. It sometimes can be lost and then backfilled, or even wrong and later corrected. In British Columbia, where I'm from, for example, our CDC does not input data on the weekends, thus this big gap in the middle. And on weekdays, cases from afternoon might be entered by the hospitals only on the next day. So this offset from the diagonal represents this type of delay. So if we run our query on such data, on Thursday we'll get 1 instead of 2, on Friday 0. In this naive approach, we're constantly getting answers wrong. But what's worse, we're also rewriting history as we go. The numbers eventually get corrected, but these corrections are not explicit. If someone complains to you about the 0 result they got on Friday, the next day there will be no trace of that left. Batch processing on event data is non-reproducible. The results you get will be changing as new data arrives, and corrections are not made explicit. What's worse, errors are concentrated in the recent results everyone cares about the most. If you're like me, you probably have already learned to ignore the downwards trends on the graphs like that. But honestly, I cannot say that it doesn't still have effect on me. I always catch myself thinking like, oh, it's a lot of errors, but maybe they are going down. My point is, data today matters a lot, and this fake trend can be the difference between imposing or lifting the lockdown. And if you try to explain this nuance to a politician, you will only end up undermining their trust in data, and the slightest doubt like that will make them fall back onto their gut feeling. I'm sure nobody wants that. So, can batch be fixed? I guess we could delay the processing entirely by 1 day, but we would also have to account for weekends where 3 days of delay is needed. Also, statutory holidays are probably causing us some problems. That's a lot of cognitive load for just one small data set, right? You probably will make a mistake somewhere. And imagine now that you need to join several such data sets that are updated on completely different cadences. Not only I can't wrap my head around this, I really don't want to. There must be a better way. The takeaway here is that batch processing is non-temporal. It relies on data completeness, so the best way for you to get accurate results is to wait for all temporal problems to disappear on their own. But then you just get results that are completely outdated. Batch pushes all the edge cases and complexity onto you. This makes it very manual. Even when properly automated, it needs a lot of babysitting. So when person walks away from this type of data pipelines, the data usually stops flowing. This is something we've seen a lot during COVID, where most of the data projects from last year around things like hospital bed occupancies became stale after volunteers who worked on them moved on, and it's really heartbreaking. The solution is stream processing. Tyler Akidaw's series of posts called Stream Processing 101 is probably the best 1 hour of time you can invest if you're curious in this topic. In stream processing, data is treated as an unbounded stream of events. Processing can run continuously and potentially forever, so there is no such thing as done state. Results are emitted as we go. This is how stream processing would handle this case. Here I changed the query a little to use Apache Flink's tumbling windows, but it's mostly the same as before. Now this is very interesting. We're getting all correct results and there is no redundant work. We're getting 1 result per day as we wanted to. Thanks to this green line, the system somehow knows when it needs to delay the processing to produce accurate results. This mechanism is called watermark, and it's pretty simple. Watermark tells us that at a certain system time, TS, with a high probability, we have observed all events prior to event time, TE. The watermark can be predictive, so system might constantly adjust it based on the observed delays in the data that is coming in. Or it can be manual as a fixed offset of end days, or what's even better, the owner of dataset can hint us that data input of a certain day has been finished, and allowing us to process data and emit the correct result. This mechanism looks super elegant to me because it reflects the true nature of data processing. All data processing is a balancing act between correctness and latency. Even if some data on Friday was lost and later backfilled, stream processing can still correct that. But most importantly, such correction will be explicit. A distinct event will be emitted telling us, hey, remember Friday? I was wrong back then. This means that retractions and corrections can be automated downstream. It's a widely accepted opinion now that stream processing is a superset of batch, a more complete and intuitive processing model. It faces temporal problems head-on instead of just ignoring them, and lets you control the trade-off between latency and correctness. The built-in handling of all corner cases makes it very autonomous. You can write query once and let it run for years. It's also very composable. The data we looked at in our example in real life would consist of thousands of datasets coming from different hospitals, and each of them could indicate to us when they finished entering data for the entire day, and let us derive the combined watermark. The way we exchange data today is simply lacking the means to make use of this model. You cannot put watermarks in a CSV. A very common misconception is that stream processing only useful for high-frequency data, but that's absolutely not the case. In Camus, we have pipelines for data that is updated once a year, and we still see a lot of benefits from using this model. So where all of this is going? In this talk I started with state data and showed how it evolved into a more event-based historical form through CDC, domain events, and event sourcing. We then saw a similar transition happen in analytics, going from Snowflake schema to ELT and data lakes. And then we looked at stream processing that have been evolving separately to handle event-based data, and is now providing better data processing tools for analytics. There are also some interesting parallels in version control and distributed ledger systems that I didn't have time to cover, but I believe the data world is converging towards something that might be the true form of data, or at least a better form of it. The way I see it is, we spent last few decades in this deep local optima of centralized batch processing, and now slowly crawling our way out of it. As we move towards event-based and continuously flowing data, it's a no-brainer that we'll be pushing analytics towards real-time speeds. For this, we'll need data processing to be fully autonomous. And the more complex processing gets, the more we'll need mechanisms to tell us exactly where every single bit of information came from, so we could trust our data. Since everyone wants to keep full control of their data, it will stay decentralized, but we will have to build interoperable data supply chains to make data globally integrated. I spent a lot of time on this topic and saw that at current rate it will take us a few more decades to get out of this local optima. So I started a project that builds from ground up in this new space, the one that I see as the future state of data. The first part of this project is Open Data Fabric, an open protocol specification for global data exchange and processing. You can think of it as a mix of Git and blockchain for data, or CSV on steroids with some streaming SQL built in. This is how ODF looks conceptually. On the left you have some source data publishers that provide data to the system. Their data flows into the graph of derivative datasets that clean, enrich, aggregate, and extract insight from data. Every one of these blue derivative datasets is just a bit of streaming SQL that can be owned and maintained by a completely different person or organization. Similarly to how you collaborate on open source software, ODF lets you collaborate with others on building decentralized data processing pipelines. And the protocol is designed to prevent and expose any malicious actions. People are kept out of this processing loop. They configure the queries, but they never touch data manually. This allows us to achieve 100% accurate reproducibility, lineage, and provenance, while also letting data flow in near real time, to be shown to decision makers and used for AI and machine learning and automation. Metadata is the first-class citizen of any ODF dataset. We actually think it's more important than data itself because without knowing where data came from and how it was transformed, you cannot really trust the data, it becomes useless. Metadata itself is also a ledger of events. It stores your queries and carries watermarks and gives data all these amazing properties like zero-cost stable references, so you never have to version or copy your data ever again for reproducibility. It also supports dataset evolution, so queries and data schemas can change without breaking the downstream pipelines. Camus CLI is a reference implementation of the ODF protocol. It's basically a world's first decentralized data warehouse that has simplicity of Git that you can run on your laptop and build complex peer-to-peer data pipelines with. It's by far the simplest way to try stream processing today because it gives you the power of Spark and Flink SQL without you spending weeks to install and configure these big frameworks. So I invite you to give it a try, and you can look up CamuCLI and watch our tutorial videos, follow our self-serve demo and a bunch of examples. And we also created a Discord server recently where you can chat with us and other people about ODF, stream processing, and reproducibility in data in general. So data is really just a record of observations. It's our modern-day history book. You don't modify version or diff history. If you're doing any of that, you're probably dealing with data in some of its derivative or projection forms, and you shouldn't be using that for your main data model. Data is rarely frozen in time or complete. It flows continuously. We should stop trying to archive it and build data pipelines instead. We should embrace the temporal problems and embrace that data processing is the balancing act between latency and correctness. Batch processing undermines trust in data. It's very manual, it creates a cascade of errors. So I think we can do better, and we should set a higher bar for ourselves and revisit how we exchange and process data. Because reproducibility, verifiability, provenance, and real-time aspects is not something we can bolt on onto the current models. And I invite everyone to collaborate with us. I believe that this next data revolution will not come from the enterprise, which for decades remained focused only on going bigger and going faster. I think it will come from open science and open data communities working together to achieve these new qualities of data.